Underfit Squad team. I'm Dũng, the lead presenter for our team, and today we are excited to share our fourth place solution for the Try My Institute problematic internet use competition. So, here is a quick look at today's agenda. Uh, let's begin with a brief introduction to our background. Uh, we are third year students at the Faculty of Information Technology, majoring in computer science, University of Engineering and Technology, Vietnam National University. We are studying machine learning as part of our coursework. Uh, this were actually our first Kaggle competition, and it was part of a major project for our machine learning course. Mm, As beginners, we did not have much experience or deep knowledge on this field. We simply applied the basic concepts we learned at school and very fortunately achieved a high rank. Now let's move on to the summary of our solution. First of all, for this project, I utilized ensemble methods. Specifically, I combined three models: XGBoost, like
Excuse me,
GBA.
sorry, one question. I'm not sure if we're seeing the right screen. I don't think your slides are moving, at least for me.
Sorry.
Right. Um,
I was seeing the PowerPoint window as opposed to the full presented view.
Oh,
yeah, is there a present option?
is
That's
is it
better.
okay now?
Yeah, perfect.
Yeah, we see the summary. Yeah. Summary slide.
Yes, so for this project, I combined three models, uh, XGBoost, GBM, and CatBoost. Here is the training and making prediction workflow. First, split the training data into 5 folds. Then for each fold, we clone and train a model. Generate predictions on the validation portion of the fold. And then each model generate prediction on the test data. This resulting in 5 different sets of predictions. We then aggregate these 5 predictions by averaging them, and then we use the predictions on the validation set to optimize the SII routing threshold, and finally apply that threshold on the test prediction. The most important features are primarily newly engineered ones. Uh, the SDS score weighted is calculated as the raw slip disturbance score multiplied by specific weights. The internet hours age is the combination of internet usage hours and age features. Uh, the physical height age is the combination of physical height and age. And this last features combines internet usage hours, total push-up and curl-up. We use the Kaggle environment, of course, along with common Python libraries for data manipulation, visualization, and model training. The data pre-processing takes about 2 minutes, and the training and making prediction takes about 4 minutes. Moving on to the feature selection and engineering process. Uh, at the beginning, the features we care the most about are age, physical columns, include BMI, weight, height, and waist circumference. Internet usage hours, the raw sleep disturbance score, and the CGAS score. So we are going to handle the missing values for these key features. For the less important columns, we chose not to fill the missing values as we found that doing so worsened the results. So for the important features, um, the missing values were filled using submodels with inputs from other reliable columns, such as the demographic features and the columns that we filled can be used again. So the submodels could be linear regression, logistic regression, or k-nearest neighbor, depending on the case. Um, we chose linear regression for waist circumference due to its linear relationship with the weight and the physical BMI. Logistic regression for the internet usage hours because it is a classification task, and just pick k-nearest neighbor for the remaining cases. Um, so we also figured out that there are no participants with an SII score of 3 who have a CGAS score greater than 80, and there are no participants with an SII score of 3 who have an SDS score less than 35. This might indicate that a CGS score of 80 and an SDS score of 35 could serve as effective thresholds for predicting who has severe problematic internet use and who does not. Therefore, we decided to assign weights for these two columns. The weights are calculated using a sigmoid function. The characteristic of the sigmoid function is that the closer the values are to the threshold, the steeper the curve becomes, allowing for clearer differentiation. So, for example, the weight for the CGS score is calculated as CGS weight of CGS score AB equals 1 over 1 plus E raised to the power of negative A times CGS minus B. So here is the plot of CGS weight. As we can see, when the CGS score is closer to 80, the curve becomes steeper. This means the weight for the CGS score changes more, enhancing its ability to aid in classification. So after we get the CGS weight, we multiplied it with the CGAS score to get the new feature, CGAS score weighted. The same technique is applied to the sleep disturbance score, resulting in SDS score weighted. Uh, for the feature engineering, we combined columns that we feel were related to each other. In total, we created 22 new features. So here is the variable importance plot. Uh, we measured feature importance using permutation importance. So the 5 most important features are as we presented earlier. And starting from the 10th features, the importance drops below 0.1, meaning that this feature might contribute less to the prediction. Um, this is the plot showing the relationship between the SDS score weighted, which is the most important feature, and the SII column. So there is a clear decreasing linear chain right here. The higher the SDS score weighted, the lower the SII values. So I know these two features are supposed to be positively correlated, meaning we would expect an increasing trend where higher SDS scores correspond to higher SII values. However, I've just found out that I made a mistake when calculate the SDS score weighted, which made this feature flipped. High SDS score became low and low SDS score became high. So therefore, we are seeing a decreasing trend right here. Mm, Despite this mistake, this feature still work effectively somehow. Next is the plot showing the relationship between internet, our age, and the SII. Uh, Internet our age is a combination of internet our use and the age feature. So the line starts by increasing, indicating that as internet usage hours and age rise, the SII values tend to go up as well. In other words, problematic internet use tends to occur when you are older and use more internet daily. And then there is a dramatic fall right here, which might reflect that problematic internet use peaks during adolescence and starts to decrease afterward. However, as we know, the data for the adult group is very limited, so we are not certain about this trend. Okay, let's keep going to our training methods. First is our model. Uh, our base model include a cat boost like GBM and XGBoost. These models were combined using a stocking regressor, which allows us to stock them and make predictions based on the results of each model. Uh, we start with our training data and initialize a stratified k-fold object to split the data into 5 folds. For each of these folds, we clone and train the model. And after training the model, making prediction on the validation portion of the fold, of the 5 folds, we have predictions for the entire training data, which is the out-of-fold prediction. We use these out-of-fold prediction to find the optimal routing threshold for routing predictions. These thresholds will be used later. So, also for each fold, the model also generates predictions on the entire test data. After completing all 5 folds, we have 5 sets of prediction from the folds by averaging them. Finally, we apply the routing thresholds to the aggregated test predictions to obtain the final prediction. Uh, let's shift our focus to the simple model. For our simple model, we used only the 5 most important features identified earlier. Mm, as mentioned earlier, our ensemble model combines 3 different models. To identify the best performing model, run uh, we run each one individually using the same workflow presented earlier, and XGBoost, despite not performing well on the public test set, it achieved the best result on the private test set overall, with a score nearly on par with the ensemble model. Ensemble model. So in conclusion, our simple model utilized only the 5 most important features, and the XGBoost model. Finally, here is an overview of our solution. Um, One of the key insights we learned during this competition was that simple approaches can actually outperform more complex methods. It was surprising because our methods were quite basic and straightforward, and we did not expect much. Yet we still managed to achieve a good result. Fortunately, another important lesson were, was not to trust the public scoreboard too much. This competition highlighted this lesson as everyone position on the public leaderboard changed significantly on the private test set. Uh, what set us apart in this competition must be the data pre-processing because the model training and the threshold optimized part is taken from the public notebooks. So it must be the careful handling and engineering of the data that made the difference. The most enjoyable part of the competition was definitely the supportive Kaggle community. The detailed notebooks and discussions were really helpful. And interestingly, our relatively limited skills turned out to be an advantage in a way, as they helped us avoid overfitting to the public test set, and we were able to focus on generalizing well on the private test set, um, which ultimately worked in our favor. So thank you so much for your attention. Let's move on to the question and answer section.